Good morning and welcome everyone. Myself, Rutanshi Patel, thanking you all for joining us today on the webinar on the topic Symmetry and Group Theory and its application in chemistry. My heartiest welcome to Dr. Paresh Patel, sir. It's our privilege that Dr. Paresh Patel, sir, is again joining with us today. So far, we have completed two sessions. Sir, thank you so much for delivering excellent subject knowledge to us. Students have learned a lot from this. And now I request Dr. Paresh Patel, sir, to continue with today's session. Over to you, Paresh, sir.
Thank you, Kusu madam and Rutansi madam. So good morning, all of you. So yesterday we discussed about the matrix representations, matrix, general introductions regarding the matrix, and how to find out the class as well as order of a group. So today we are going for the matrix representations for different symmetry operations or matrix notations for the geometrical transformations. So how to get the matrix representations for the different symmetry operations? First of all, find out the symmetry elements are present in a molecule and operated symmetry operations on the vectors of the molecules and find out the changes, and that changes can be represented in form of the matrix that can be represented as a matrix representations for the different symmetry operations. So how to get the matrix for the different symmetry operations? So first of all, we're going for the identity symmetry operation. Okay, first symmetry operation is identity. Okay, now if you operate identity symmetry operation on any molecule, we know that there is no change in the position of the vectors. So when a point with the coordinates x, y, z subject to identity operation, so it new coordinates will be the same. So if you go for the e into x is equal to 1 into x plus 0 into y plus 0 into z. E into y 0 into x plus 1 into y plus 0 into z. E into z is equal to 0 into x plus 0 into y plus 1 into z. So this can be represented E x y z is equal to 1 0 0 0 1 0 0 0 1 and x y and z. It means the matrix representation for identity symmetry operation can be represented as 1 0 0 0 1 0, and this is the derivation for the identity symmetry operations. Now second symmetry operation is proper rotation. Second symmetry operation is proper rotation. First of all, if you go for the anti-clockwise, okay. Now, in case of the matrix representations, if we operate different symmetry operations on a two-dimensional vectors and find out the changes, and that changes can be extended into three-dimensional ways. Suppose vector t with the coordinates x and y. It means along the x-axis the distance is x. This is x-axis, this is y-axis. And along the y-axis the distance is y. Okay. Now vector t with the length r and coordinates x and y. It means along the x-axis the distance is x and along the y-axis the distance is y. Now, first of all, anti-clockwise rotation. In this one, this is the right angle, so we can assign that, and angle is phi. Suppose angle along the axis is phi, so we can represent cos phi is equal to cos phi is equal to base divided by hypotenuse. So x divided by r. So x is equal to r cos phi. Sin phi is equal to opposite side divided by hypotenuse. So front side it means y divided by hypotenuse is equal to r. So y is equal to r sin phi. Now, if you go for the anti-clockwise rotation, so P becomes P dash with the new coordinates x and x dash and y dash, and the distance remains as it is. Now, along the x-axis, this distance may be x dash, and along the y-axis, the distance is y dash. Okay, and the angle is theta. Now, if you rotate this vector P around theta, so P becomes P dash with the new coordinates x dash and y dash. So this can be represented as again right angle. So cos phi is equal to cos phi plus theta. Now the new angle is, the overall result is phi plus theta. So cos phi plus theta is equal to base divided by hypotenuse. Base is x dash and hypotenuse is r. Similarly, sin phi sin phi plus theta is equal to front side divided by hypotenuse y dash by r. Cos phi plus theta is equal to x dash by, or we can say x dash is equal to r cos phi plus theta. X dash is equal to, we know that cos a plus b is equal to cos a cos b minus sin a sin b. So r cos phi cos theta minus r sin theta sin phi. So x this is equal to, we know that the value of r cos phi is equal to x. So x cos theta minus r sin theta is equal to y, r sin theta. Okay, so this is the one equation. Similarly, if you go for the y dash is equal to r sin phi plus theta, sin a plus b is equal to sin a cos b plus sin b cos a. Similarly, y dash is equal to r sin phi cos theta plus r cos phi sin theta is equal to, y is equal to, we know that the value for r sin phi is equal to y cos theta plus r sin theta, it means r cos phi is equal to x, it means x sin phi, or we can represent it as y dash is equal to x sin theta plus y cos theta. Now, now we have two equations. One is with related to x dash and another one is related to y dash. So x dash and y dash. Now we can write this both this equation x dash and y dash in form of the matrix as a x dash y dash is equal to x means cos theta minus sin theta, and over here sin theta and cos theta. X and y. So this is the CNK anti-clockwise. So this is P dash and P. So where CNK anti-clockwise is equal to cos theta minus sin theta, cos theta. Now this is two-dimensional system. We can extend it up to three-dimensional system is equal to cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. So this is the matrix representations for clockwise rotation. Now if we put the value theta is equal to 180, 120, depends upon the that rotation to give the matrix for the proper rotation. Okay, so anyhow, this is the equation for the anti-clockwise rotation. Now, if you go for the clockwise rotation, matrix representations for the clockwise rotation. This is x-axis, this is y-axis. Okay, so angle is phi. So the vector p with the coordinates x and y, the length of this vector is r. Now, the vector p with the coordinates x and y, it means along the x-axis the distance is x, and along the y-axis the distance is y. Okay, this is right angle. So cos phi is equal to base divided by hypotenuse. So x divided by r. So x is equal to r cos phi. Sin phi is equal to front side divided by hypotenuse. So front side is the y divided by hypotenuse. So y is equal to r sin phi. Now this is the clockwise rotation, matrix representations for clockwise rotation. So if we rotate this vector p to p dash, this is clockwise rotation with the coordinates x dash and y dash. So x becomes x dash and y becomes y dash. Okay, now here this is the rotation from p to p dash, and this is the theta. It means this angle is phi minus theta. Okay, so cos phi minus theta is equal to base x dash divided by hypotenuse r. Similarly, sine phi minus theta is equal to y dash by r. Why y dash by r? Front side divided by hypotenuse. So x dash is equal to r cos phi minus theta. We know that cos a minus b is equal to cos a cos b minus sin a sin b. It should be plus. So x this is equal to r cos phi cos theta minus r sin theta, r sin phi and sin theta is equal to r cos phi is equal to x cos theta minus y sin theta. So this is the one equation regarding the x this. Similarly, y this is equal to r sin phi minus theta. We know that sin a minus b is equal to sin a cos b minus should be plus cos a sin b. So y this is equal to r sin phi cos theta plus minus r cos phi sin theta. Y this is equal to the value for r sin phi is equal to y cos theta minus r cos phi is equal to x sin theta. So y this is equal to minus x sin theta plus y cos theta. So this is the equations we did to x dash and y dash. Now we can write both this equation in form of the matrix x dash and y dash. X dash matrix x dash and y dash is equal to cos theta sin theta minus sin theta. So just a minute. Yes, minus sin theta cos theta x and y. This is p dash p, this is k and k, and clockwise. So where c and k clockwise can be represented as cos theta sin theta minus sin theta cos theta. This is the two-dimensional system. We can extend it up to three-dimensional system. So C and K clockwise cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So this is the matrix representations for clockwise rotation. Now if we put the value theta is equal to rotational axis of symmetry to give the matrix representations for the clockwise. So these are the two derivations for the proper rotation, either anti-clockwise or clockwise. Now in case of the water molecule, we know that water molecule consists E, C2 sigma Vx sigma Vy symmetry elements. Now, if we operate C2 symmetry operations, or how to get the matrix representations for the water molecule, we know that in case of the water molecule, we have to rotate the molecules around 180. If you go for the clockwise rotation, then put the value theta is equal to 180, cos 180, sin 180, 0, minus sin 180, cos 180, 0, 0, 0, 1. So is equal to value for cos 180 is equal to minus 1, sin 180 0, 0, 0, minus 1, 0, 0, 0, 1. So this is the matrix representations for C2 for clockwise rotation. Similarly, in case of the anti-clockwise, if we put the value 180, so matrix will be the same in case of water molecule. Why? So if you rotate the water molecule around clockwise or anti-clockwise around 180 to give the same matrix. Now, next one is matrix representations for reflection operation. Third one is reflection operation. Now, how to get the matrix representations for the reflection operation? This is a two-dimensional system x and y with the coordinates p, x, and y. The length is r, x, and y. Now, if you go for the reflection of the vector p along this axis, the resultant matrix will be the p dash. Now, in case of reflection, so there is no change in the y-axis, but there is change in the x becomes minus x. So this can be represented as x this is equal to minus 1 into x plus 0 into y. Y this is equal to 0 into x plus 1 into y. So along the x-axis, x becomes minus x, and there is no change in the y. And along the y-axis, y becomes y. It means this can be represented as 0 into x plus 1 into y. Now, these two equations can be represented in form of the matrix as x dash y dash is equal to minus 1, 0, 0 into y. X and y. This is p dash, this is p. Now, in case of this reflection through this plane, it means this plane is perpendicular to the x. It means this plane is sigma yz. Okay, sigma yz plane. So sigma yz is equal to minus 1, 0, 0, 1. Now this is two-dimensional system. We can extend it up to three-dimensional system. Sigma yz is equal to minus 1, 0, 0, 0, 1, 0, 0, 0, 1. So see, this is the matrix representations for the sigma yz. Similarly, we can go for the sigma xz is equal to 1, 0, 0, 0, minus 1, 0, 0, 0, 1. And sigma xy is equal to 1 0 0 0 1 0 0 0 minus 1. So this is the matrix representations for sigma xy. Now for symmetry operation is improper axis of symmetry. And that can be represented as a SNK. And SNK is equal to CNK into sigma h. Okay, this is clockwise rotation, and we know that the matrix representations for the clockwise rotation sine theta 0 minus sine theta cos theta 0 0 0 1. Now in case of sigma h means this is horizontal plane to the main principal axis, and we can consider that main principal axis on z axis. It means this plane should be sigma xy plane. And that can be represented as cos theta sine theta 0 minus sine theta cos theta 0 0 0 1. And matrix representations for sigma xy can be represented as 1 0 0 0 1 0 0 0 minus 1. Now combination of two matrices to give cos theta sine theta 0 minus sine theta cos theta 0 0 0 minus 1. So this is the matrix representations for improper axis of rotation. The last one is matrix representations for center of symmetry. Or we can say point of a symmetry or inversion of a symmetry. Now suppose x, y, and z are the coordinates of the vector p, and if we operate center of symmetry or point of a symmetry to give x this is equal to minus 1 into x plus 0 into y plus 0 into z. Y this is equal to 0 into x minus 1 into y plus 0 into z. Z this is equal to 0 into x plus 0 into y minus 1 into z. So x this, y this, z this is equal to minus 1 0 0 0 minus 1 0 0 0 minus 1 x, y, and z. So p dash p, and this is the matrix representations for center of symmetry or inversion of operation. Inversion operations can be represented as minus 1 0 0 0 minus 1 0 0 0 minus 1. Okay, so these are the matrix representation or derivations of different symmetry operation. Matrix representations for the different symmetry operations. Now how to represent matrix representations for water molecule. We know that water molecule consists E C2 sigma V XZ sigma V YZ symmetric elements. So matrix representations for identity we already discussed 1 0 0 0 1 0 0 0 1. Now matrix representation for C2. Now in case of water molecule, if you rotate these molecules around 180 along this axis, either clockwise or anti-clockwise, both are the same. So result will be the same. So matrix representations for clockwise rotation or anti-clockwise to give the same matrix. So first of all, if you go for the matrix representations for the anti-clockwise rotation, and that equation is cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. So this is the matrix representations for anti-clockwise. So in this case, if we put the value theta is equal to 180, so cos 180 minus sine 180, 0, sine 180 cos 180, 0, 0, 0, 1 is equal to, we know that value for cos 180 is equal to minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. So this is the matrix representations for C2 if we take the equation for the anti-clockwise. Now if we take equation for the clockwise, so cos theta sine theta 0 minus sine theta cos theta 0, 0, 0, 1 is equal to cos 180 sine 180, 0, minus sine 180 cos 180, 0, 0, 0, 1 is equal to minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. So this is the matrix representations for C2 symmetry operation, either anti-clockwise or clockwise. The result will be the same. So anyhow, matrix representations for C2. Can be represented as minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Now sigma b xz is equal to 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Sigma b yz is equal to minus 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so this is the matrix representations for water molecule, or we can say matrix representations for identity C2, sigma Vxz and sigma Yz, matrix representations for water molecule. Now, next one is matrix representations for ammonia molecule. We know that ammonia molecule consists E C3 plus C3 minus sigma Va, sigma Vp and sigma Vc symmetric elements. Now matrix representations for identity 1, 0, 0, 0, 1, 0, 0, 0, 1. Matrix representations for C3 plus. It means one time clockwise rotation. So if we put the values in a clockwise rotation, cos 120, sine 120, 0, minus sine 120, cos 120, 0, 0, 0, 1 is equal to value for cos 180, 120 is equal to minus 1 half, sine 180 root 3 by 2, 0, minus root 3 by 2, minus 1 half, 0, 0, 0, 1. So this is the matrix representations for C3 plus. Similarly, C3 minus. C3 minus means one time anti-clockwise rotation around 120. So cos 120 sine minus sine 120, 0, sine 120 cos 120 0 0 0 1 is equal to minus 1 half minus root 3 by 2 0 root 3 by 2 minus 1 half 0 0 0 1. So this is the matrix representations for C3 minus. C3 minus, this is the matrix representations for anti-clockwise rotation. This is for C3 minus. Now sigma Va. In case of ammonia molecule, we have to remember that all these vertical planes, Va, Vb, Vb, sigma Va, sigma Vb, sigma Vc, all are the visor planes. It means the matrix representation for sigma Va is equal to minus 1 0 0 0 1 0 0 0 1. Similarly, sigma Vb is equal to minus 1 0 0 0 1 0 0 0 1. And similarly for sigma Vc is equal to minus 1 0 0 0 1 0 0 0 1. So these are the matrix representations for ammonia molecules as a sigma V E identity C3 plus C3 minus sigma Va sigma Vb sigma Vc. Now we are going for the laws of four laws of a group. There are four laws of a group. First law is a law of identity. What is law of identity? Combination of identity symmetry operation with any symmetry operation, answer will be the same. As for example, water molecule consists E, C2, sigma Vx and sigma V visor symmetric elements. So if you go for the E into C2 is equal to C2 into E is equal to C2. Now left hand side is equal to E into C2 1 0 0 0 1 0. So this is the matrix representations for identity. And for C2, we know that minus 1 0 0 0 minus 1 0 0 0 1. So if you go for the combination of both these matrices, answer will be the minus 1 0 0 0 minus 1 0 0 0 1. And right hand side is equal to C2 into E is equal to minus 1 0 0 0 minus 1 0 0 0 1 and identity 1 0 0 0 1 0 0 0 1 to give minus 1 0 0 0 minus 1 0 0 0 1 is equal to C2. Okay, so what is the law of identity? Combination of any symmetry operation with identity answer will be the same. Next one is law of combination or multiplication. Law of combination or multiplication. What is law of combination? Combination of any two symmetry operation. Answer will be the third element of the same group. As for example, C2 into sigma Vxz is equal to sigma Vyz. So left hand side is equal to C2 into sigma V xj. Matrix representation for C2 minus 1 0 0 0 minus 1 0 0 0 1. Sigma V xj 1 0 0 0 minus 1 0 0 0 1 is equal to combination of these two matrices minus 1 0 0 0 1 0 0 0 1 and is equal to sigma V 1 z. So left hand side is equal to right hand side. So law of combination of any two symmetry operation, answer will be the third element of the same group. Third law is law of association. What is law of association? C2 into sigma V xj into sigma V yz is equal to C2 into sigma V xz into sigma V yz. So left hand side is equal to C2 into sigma V xz into sigma V yz. Now matrix representations for C2 minus 1 0 0 0 minus 1 0 0 0 1. Sigma V xj 1 0 0 0 minus 1 0 0 0 1 and minus 1 0 0 0 1 0 0 0 1. So first of all we have to go for the combination of these two matrices. So minus 1 0 0 0 1 0 0 0 1 and then combination with minus 1 0 0 0 1 0 0 0 1. Answer will be the 1 0 0 0 1 0 0 0 1. This is the resultant matrix. Now, if we go for the right hand side, C2 into, it means first of all we have to go for the combination of these two matrices. Is equal to minus 1 0 0 0 minus 1 0 0 0 1. It remains as it is. Now combination of these two matrices minus 1 0 0 0 minus 1 0 0 0 1 is equal to combination of these two matrices 1 0 0 0 1 0 0 0 1. So right hand side is equal to ls, left hand side is equal to right hand side. It means C2 into sigma Vx into sigma Vy is equal to C2 into sigma xz and yz. And last law of group is law of inverse. What is law of inverse? Any symmetry operation and its inverse, answer will be the identity. As for example, C2 into C2 inverse. Okay, C2 or C21 both are the same. Is equal to identity. Now, in case of left hand side is equal to C2, it means minus 1 0 0 0 minus 1 0 0 0 1. C2 inverse minus 1 0 0 0 minus 1 0 0 0 1. Now combination of these two matrices, answer will be the 1 0 0 0 1 0 0 0 1 is equal to right hand side, or we can say identity. So these are the four laws of the group. Now we're going for the most important title of our exams, and that is reducible and irreducible representations. Reducible and irreducible representation. Let A, B, C, D, P. These are the different matrices of the representations. Let P be the similarity transformations. And if you go for the P dash into P is equal to A dash. P dash B into P is equal to B dash. P inverse C into P is equal to C dash. P inverse D into P is equal to D dash. Okay. A, B, C, D, P. These are the matrix representations of a particular representations. Now P with the similarity transformations. So A becomes A dash, B dash, C dash, and D dash. And suppose A dash can be represented as A1 0 0 0 0 0 A2 0 0 0 0 A3 0 0 0 0 A4. Now we can reduce higher dimension matrix into lower dimension matrix, so that representations can be represented as a reducible representations. So what is reducible representations? If you reduced higher dimension matrix into lower dimension matrix, so that representations can be represented as reducible representations. And if we can't reduce higher dimension matrix into lower dimension matrix, so that representations can be represented as a irreducible representations. First example is the water molecule. Water molecule consists four different symmetry elements: E, C2, sigma Vx, sigma Yz, and sigma Yz. Now, matrix representations for identity can be represented as C2 can be represented as -1 0 0 0 -1 0 0 0 1. Sigma Vxj can be represented as 1 0 0 0 -1 0 0 0 1. Sigma Vyz is equal to -1 0 0 0 1 0 0 0 1. These are the four matrices for the water molecule. Now, we have to remember that the dimension of any representation depends on the matrix representations for the identity symmetry operation. Okay, so with the help of identity, we know that the dimension of this matrix is a three-dimensional matrix. So this representation is a three-dimensional representations. Okay, now this is the three-dimensional matrix. We can reduce this three-dimensional matrix into lower dimensional matrix. So that representations can be represented as a reducible representations. Okay, so these are the four matrices, and these representations can be recognized as reducible representations. Why? We can reduce this three-dimensional matrix into lower dimensional matrix. So how to reduce this higher dimensional matrix into lower dimensional matrix? E C2 sigma Vxz sigma Vyz. X, Y, and Z. Now, this is with respect to X. It means matrix 1. With respect to Y, and this respect to Z. Similarly, C2. This respect to X, -1, matrix -1, matrix -1, and 1. Sigma Vxj, 1, -1, and 1. Similarly, Yz, -1, 1, and 1. Okay. So these are the reducible representations. Now, we can't reduce one dimensional matrix into lower dimensional matrix. So these representations can be recognized as irreducible representations. So what are reducible and irreducible representation? We can reduce higher dimensional matrix into lower dimensional matrix. So that representations can be represented as a reducible representations. Okay. Now in this case, this is the reducible representation and these are the irreducible representations. We can't reduce higher one dimensional matrix into the lower dimensional matrix. So these representations can be recognized as a irreducible representations. Second example is the ammonia molecule. We know that matrix representations for identity symmetry operations can be represented as 1 0 0 0 1 0 0 0 1. C3 plus C3 plus minus 1 half root 3 by 2 0 minus 1 half minus root 3 by 2 minus 1 half 0 0 0 1. This is the matrix representations for clockwise rotation. C3 plus C3 minus is equal to minus 1 half minus root 3 by 2 0 root 3 by 2 minus 1 half 0 0 0 1 and sigma VA minus 1 0 0 0 1 0 0 0 1. Similarly, sigma VB minus 1 0 0 0 1 0 0 0 1. Sigma VC is equal to minus 1 0 0 0 1 0 0 0 1. Now, the dimension of this matrix is equal to 3. Why? The representations, the dimension of any representation depends on the matrix representation for the identity symmetry operations. So this is three-dimensional matrix, means this is the mm, three-dimensional representations. Now we can reduce these three-dimensional representations into smaller dimension matrix. So this representation can be represented as a reducible representation, or we can say these are the matrix representations for the reducible representations. Now we can reduce this three-dimensional matrix into two-dimensional and one-dimensional. In case of the ammonia molecule, uh, we have to operate symmetry operation on the x and y as a simultaneously. So we can't separate x and y. So we have to reduce it just like this one, two-dimensional and one-dimensional. E C2 sigma V xj 1 0 0 1 minus 1 half root 3 by 2 minus root 3 by 2 minus 1 half. Similarly, sigma Vx minus 1 0 0 and 1 and z 1 1 and 1. We can also take this one. Why? The character of minus 1 half is equal to minus 1. Okay. So anyhow, these are the reducible representations and these are the irreducible representations for ammonia molecule. Now, relationship between reducible and irreducible representations. This is the equation Ni is equal to 1 upon H summation R, character R into N, character I into R. This is the equation And with the help of this equation, we can reduce reducible representations into irreducible representations. Here n I is equal to numbers of time that symmetry, numbers of time that irreducible representations. H represents order of a group. Yesterday we already discussed this, that order of a group is nothing but the numbers of symmetry elements are present in a molecule. This is the summation of character R into R. It means character for reducible representations. And represents number of time that symmetry operation. Character I into R, it means this is the character for reducible representations. Okay, with the help of this equation, we can reduce reducible representations into irreducible representations. Suppose one representations for C3b group R E twice C3 twice sigma V. Five 2 minus 1. This is the reducible representations, and with the help of E twice C3 thrice sigma V, A1, A2, E, 1, 1, 1, 1, 1 minus 1, 2 minus 1, 0. This is given. This is the character table for C3b point group. This is given to you to reduce this higher dimension matrix into lower dimension matrix. This is reducible representations. Why reducible representations? The dimension of this matrix is 5. So we can reduce this 5-dimension matrix into lower dimension matrix with the help of this equation and character table. This character table is given to you. Now, first of all, we have to go for the values for n1, n2, and n3. n1 which corresponds to a1, n2 which corresponds to a2, and n3 which corresponds to e. So first of all, n1 is equal to 1 upon h. H represents order of a group. Now order of a group is equal to number of symmetry elements are present in a molecule. So here identity as a 1, 2, and 3. It means order of a group is equal to 3. So order of a group can be represented as a 6. Summation order of a group H is equal to 6. Now, then we have to go for the summation of character for reducible representation. This is the character for reducible representations, and is equal to number of time that symmetry operation 1. It means 5, 1, and 1. This is the irreducible representations, character for irreducible representations. So 5 is a reducible, 1, and this 1 is a irreducible, plus 2, 2, and 1, plus minus 1, 3, 1. Okay, so let us start first with the which corresponds to A1. Okay, so 5 is a reducible, number of symmetry operation is 1, and number of character for reducible representation is 1. Again, reducible representation, number of symmetry operations, and character. Okay, so is equal to 1 by 6, 5 plus 4 minus 3 is equal to 6 is equal to 1. So n1 is equal to 1. Value for n1 is equal to 1. Now similarly for n2. One by 6. Now which corresponds to A2 irreducible representations. 5 for reducible, 1, and again 1, plus 2, 2, 1, plus minus 1, 3, and 1 is equal to 1 by 6, 5 plus 4 minus 3 is equal to 1. It means n2 is equal to again 1. 4 and 3. Just a minute. N2. 5, 5, 1, 1, 5. 2, 2, 1, it means plus 4. Here minus 1, 3 minus 1 is equal to 3 is equal to 2. So N2 is equal to 2. Next one is N3. 5, 2. 5 2s are 10 plus 2 2s are 4 minus 1 minus 4 and 0 is equal to 1. It means value for N3 is equal to 1. N3 is equal to 1. So N1 is equal to 1, N2 is equal to 2, N3 is equal to 1. C3V E twice C3 3 sigma V. N1 is equal to 1 means A1 is only one time. N2 is equal to 2. It means A2 can be represented as a 2 times. And N in 3 is equal to 1. It means E is only one time. So these are the irreducible representation. We can calculate that 1 plus 1 plus 1 plus 2 is equal to 5. 1, 1, 1, 1, 2 minus 1. Okay. So these are the irreducible representations of these reducible representations with the help of this character table. Now we are going for the most important theorem, that is great orthogonal theorem. Great orthogonal theorem is concerned with the element of the matrices and which constitute the irreducible representations. The mathematical statement of the great orthogonal theorem is as follows. Okay, exam point of view, this is most important theorem. So great orthogonal theorem is concerned with the element of the matrices and which constitute the irreducible representations. The mathematical statement of the great orthogonal theorem can be represented as to a summation of to I R M N P J R M dash N dash is equal to, this is complex conjugation, H divided by LILJ and delta IJ delta MM dash delta NN dash. Here H represents order of a group, LILJ represents dimension of this matrices. This is the element of the nth row and column of the ith irreducible representations. This is the element of the m-des row and des column of the jth irreducible representation, or we can say this is complex conjugations. Now we can apply this mathematical statement to the orthogonal as well as normalized wave function. So with the help of this orthogonality, we can subdivide this mathematical statement into three mathematical statements as a character summation of TIRMN Tj r mdes ndest is equal to 0, where I is not equal to G. It means element of the corresponding matrices of the different irreducible representations are orthogonal. Elements of the corresponding matrices of the different irreducible representations are orthogonal. Now, second mathematical statement is TIR MN TJR TI is equal to 0, where M is not equal to M dest, N is not equal to N dest. Elements of the different sets of matrices of the same irreducible representations are orthogonal to each other. Elements of the different sets of the matrices of the same irreducible representations are orthogonal. And lastly, character R, TIR, MN, TJR, MDEST is equal to H by Li. This is possible only if the values for delta Ij is equal to delta MMDEST is equal to delta NNDEST is equal to 1 and Li is equal to Lj. If Li is equal to Lj, it should be square root Li square. So is equal to Li. So this is the mathematical statement of the great orthogonal theorem, and these are the three sub-mathematical statements of the great orthogonal theorem. With the help of the great orthogonal theorem, we can derive 5 consequences of this great orthogonal theorem. So first, consequences of the great orthogonal theorem, or we can say characteristics of the irreducible representations. The numbers of irreducible representations is equal to numbers of classes of the operation of a group. So first consequences of the great orthogonal theorem, the number of irreducible representations is equal to numbers of the classes of a group. As for example, number of irreducible representations. Water molecule consists E C2 sigma Vx sigma Vy symmetry elements. Now in this case, E is conjugate to itself to form an individual class, C2 conjugate to itself to form an individual class, sigma Vx conjugate to itself to form an individual class, sigma Vyz conjugate to itself to form an individual class. Okay, so in case of the water molecule, numbers of the classes is equal to 4. So that should be the 4 different irreducible representation. So whenever we talk about the character table, T1, T2, T3, and T4. Okay, so what is the rule number first? The numbers of irreducible representation is equal to numbers of classes of a group. This is the first rule. Second rule, the sum of the square of the dimension. The sum of the square of the dimension is equal to order of a group. So as for example, this is C2V group, E C2 sigma Vxz sigma Vyz. A1, A2, B1, B2. 1, 1, 1, 1, 1, 1 minus 1 minus 1, 1 minus 1 minus 1, 1, 1 minus 1. Okay. So characteristics number 2, or we can say second consequences of orthogonal theorem, the sum of the square of the dimension The sum of the square of the dimension is equal to order of a group. And always we know that dimension which corresponds to matrix representations for identity symmetry operations. So we can represent that L1 square, L2 square plus L3 square plus L4 square is equal to R, order of a group. In case of the water molecule, order of a group is equal to 4. Now this equation can be satisfied. Negative dimension is not possible. So minimum dimension is 1 possible. 1 square, 1 square, 1 square, 1 square. So is equal to 4. So rule number second is the sum of the square of the dimension is equal to order of a group. Characteristics or rule number 3. The sum of the square of the character. The sum of the square of the character is equal to order of a group. As for example, this is even irreducible representation. Sum of the square 1 into 1 square, 1 into 1 square, 1 into 1 square, 1 into 1 square is equal to 4. It means the sum of the square of the character is equal to order of a group. Here, order of a group is equal to 4. It means 1 into 1 square, 1 into 1 square, 1 into 1 square, 1 into 1 square is equal to 4. Rule number 4. This is the character of the irreducible representations of the same group are orthogonal. Suppose A1 and A2, these are the two irreducible representations. These are orthogonal. It means combination and summations is equal to 0. So 1 into 1 into 1 is equal to 1. 1 into 1 into 1, 1. Minus 1, 1 into 1, minus 1. Minus 1, 1 into 1, minus 1 is equal to 0. So any two irreducible representations are orthogonal to each other. And last consequences or characteristics of the irreducible representations. The character of the element of the same class of an irreducible or reducible representations are the same. So with the help of these consequences or characteristics of the irreducible representations, we can derive the character table for C2V point group and C3V point group. So two character tables are in our syllabus. One is character table for C2V point group and another one is character table for C3V point group. Now what is character table? The devices can be utilized in the applications of group theory and molecular symmetry is known as character table. So remember, dear students, what is character table? The devices can be utilized for the applications of group theory and molecular symmetry is known as character table. Now, first of all, character table for water molecule, sulfur dioxide molecule, H2S molecule, all are the same. Construct a character table for C2V point group or construct a character table for water molecule or construct a character table for sulfur dioxide molecule or construct a character table for H2S molecule, all are the same. So let us start with the construct a character table for C2V point group. Let us consider water molecule. It belongs to C2V point group and it consists E C2 sigma Vx z sigma Vy z. Okay. Now we already discussed about the character table for C2V. E C2 sigma Vx z sigma Vy z. A1, A2, B1, B2. 1, 1, 1, 1. 1, 1, minus 1, minus 1. 1, minus 1, 1, 1. 1, minus 1, 1, minus 1. This is the answer of this character table. So let us start with the construct the character table for C2V point group. Let us consider water molecule. It consists E, C2, sigma Vx z and sigma Vy z symmetry elements. Now, it belongs to C2V point group. E conjugate to itself from individual class, C2 conjugate to itself from individual class, sigma Vx z conjugate to itself conjugate to itself as an individual class. Sigma v y z conjugate to itself to form an individual class. Here, numbers of the classes is equal to 4. So according to the rule number first, E C2 sigma Vxz sigma Vyz. According to the rule number first, the numbers of irreducible representation is equal to numbers of classes. So we can go for T1, T2, T3, T4. This is the rule number first. Second rule, the sum of the square of the character, the sum of the square of the dimension is equal to order of a group. Okay, suppose L1, L2, L3, L4. So L1 square plus L2 square plus L3 square plus L4 square is equal to order of a group. This is the second rule. Now, here order of a group is equal to 4. Why? 1, 1, 1, 1. Okay. Now, negative dimension is not possible. So, minimum 1 is required. 1 square plus 1 square plus 1 square plus 1 square is equal to 4. So, this representation should be 1, 1, 1, 1. Suppose this one is character 1 C2, character 1 sigma V xz, character 1 sigma V yz. Rule number 3, the sum of the square of the character is equal to order of a group. So 1 into 1 square, 1 into sigma 1 plus character 1 C2 square, 1 sigma V xz square, character sigma V yz square is equal to 4. Okay. To maintain the uniformity of any character table, so first representation should be with respect to 1. If you put the value 1, it should be satisfied. It means first character for the first irreducible representation with respect to plus 1. Now, second irreducible representations, character 2 C2, character 2 sigma V xz, character 2 sigma V yz. According to the rule number 3, any two irreducible rule number 4, any two irreducible representations are orthogonal to each other. Suppose T1 and T2. So 1 into 1 into 1 is equal to 1. 1 into 1 into 1, it means character 2 C2. 1 into 1 into 1, character 2 sigma V xz plus character 2 sigma V yz is equal to 0. Now this equation can be satisfied if the character for any two irreducible representation is equal to -1 and remaining is 1. Suppose this one is 1, -1 and -1. This can be satisfied. And this can also satisfy the rule number 3. The sum of the square of the character is equal to order of a group. It means second irreducible representation should be 1, -1, -1. Now similarly, if you go for the third irreducible representations, character 3 C2, character 3 sigma Vxz, character 3 sigma V yz. Now, any two irreducible representations are orthogonal to each other. So if you go for the T1 and T3 and T2 and T3. So first of all, T1 and T3. 1 into 1 into 1 is equal to 1. 1 into 1 into character 3 C2 plus character 3 sigma V xz plus character 3 sigma V yz is equal to 0. And T2 and T3, then 1 plus character 3 C2 minus character 3 sigma V xz minus 3 character sigma V yz is equal to 0. Now add equation 1 into, so both are cancelled out. So 2 plus 2 character 3C is equal to 0. It means character 3C2 is equal to -1. Now substitute this value in the above equation. So 1 minus 1 plus character 3 sigma vxz plus character 3 sigma yz is equal to 0. So character 3 sigma vxz is equal to minus character 3 sigma vyz, or we can say 1 is equal to minus 1. It means when the value for character sigma 3 vxz is equal to plus 1, the character 3 sigma vyz should be minus 1. So if we take plus 1, it should be minus 1. Now for the fourth irreducible representation, this is fourth character C2, fourth character sigma Vxz, character 4 sigma Vyz. Again, rule number 4, any two irreducible representations are orthogonal to each other. So first of all, if we go for the T1 and T4, so 1 plus character 4 C2 plus character 4 sigma Vxz plus character 4 sigma Vyz is equal to 0. And if you go for the T2 and T4, 1 plus character 4C2 minus 4 character sigma Vxz minus 4 character sigma Vyz is equal to 0. So 2 plus 2 character 4C2 is equal to 0. It means character 4C2 is equal to minus 1. Now substitute this value in above one equation to give 1 plus character 3C2, sorry, character 4C2 plus character 4 sigma Vxz plus character 4 sigma Vyz is equal to 0. So if we take 1, so character 4 sigma Vxz plus character 4 sigma Vyz is equal to 0. It means character 4 sigma Vxz is equal to minus character 4 sigma Vyz is equal to minus 1. It means when the value for sigma Vx is equal to minus 1, it should be plus 1. So minus 1 and 1. Okay. Now, Mulliken symbol. How to derive the Mulliken symbol? Okay. So remember that any dimension is one dimensional. Capital letters A and B can be used for two-dimensional representations, one-dimensional, two-dimensional, and three-dimensional. For the two dimensionals, and three-dimensional, E can be used. Okay, here, this is one-dimensional, 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 and one-dimensional. Okay, when our representation is one-dimensional, capital letters A and B can be used. But when A and when B, so if the character for the main principal axis is plus 1, so character 1, capital letter A can be used. If the value for character is minus 1, then capital letter B can be used. So here 1 it means A, 1 it means A, minus 1 means B, minus 1 means B. Okay, now subscript. Now C2 is perpendicular to the main principal axis and the value of that character is plus 1. The subscript 1 can be used. But if there is no perpendicular axis, so we have to go for the next one. So this is the C2 and it next one is this one. So here character is plus 1, so 1 can be used, minus 1, 2 can be used, 1 can be used, 2 can be used. Okay, so anyhow, this is the character table for C2B point group. Okay, so dear students, I think this is the enough for today's discussion. So thank you very much for listening me very silently. So we will meet on the next and last lectures for the remaining portions, particularly character table for C3V point group and the applications portion. So thank you very much once again. Thank you very much.